Okay, kid. So we're gonna try doing this. I'm gonna try doing this a couple of ways. Until we kind of dial in where what the schedule looks like. So looking at that list of topics, it looks to me like if we're following your list, it will be somewhat out of order from the the textbook. So your topics and learning outcomes starts with derivative of inverse functions, hyperbolic functions, and then goes to areas between curves. So what I was thinking I would do is I would approach this in two ways. One is to kind of pick up um, from where you would have left off in Calc 1, which, if you'll recall, finishes up with it was chapter 6 for us. Um, and that was applications of integration, and that coincides with your chapter 6. And then the uh, logarithmic, exponential, and hyperbolic functions then are chapter 7. So what I'm going to do is kind of do both of those, and once you know the schedule, we can kind of dial it in. Okay, so let's start out with um, we'll actually start out with the applications of integration, and then we'll kind of and then we'll do another one on the logarithmic and exponential functions. Okay, so the applications of integration, the first couple of sections were on um, rates, and so finding um, regions between curves, first of all, and then velocity and net change. And then that's kind of where we leave off. And then uh, the next chunk of material would have been on um, uh, finding volumes. And there are um, some tricks of finding volumes that we're going to that we'll talk about. So let's dive in then with the volume by slicing. And this is a technique that you're going to see in a a lot of different a lot of different applications. So much of the different volume methods all kind of boil down to finding a volume of a cross section or a piece, and then adding a bunch of those up. And then when you take the limit, it turns into an integral. So what we have is we're going to suppose that we have a an object here. So suppose we have a solid object, and this object extends in along an axis. So let's say the x-axis. So it extends along this axis from x equals a to x equals b. Just kind of a generic solid object, such as the one shown here. Now, what we're going to do is we're going to do the partition method, the same thing that we did when we first uh, introduced the integral, right? We first introduced the integral by, let me jump to a camera here. If you remember, right, we first introduced the integral. We had this curve and the x-axis, and this is y. And so here's our curve, f of x. And we said, all right, we wanted to find the area underneath the curve from x equals a to x equals b. And so what we were going to do is we were going to chop AB up into pieces, and then we were going to find, right, make a box on each piece, And we're going to add all those up, and that's going to, in the limit, give us the integral f of x dx, and that's the area underneath the curve over the interval AB. Okay, well, we're doing that same thing here, but here we have a solid instead of the curve, and now we want to find the volume, but we're going to do the same idea, which is we're going to chop up the interval AB into pieces again. So we're going to cut it up into n subintervals, and each one is going to have width delta x. And that's just the endpoint B minus A over the number of endpoints. And so what that does is our interval A to B here, this is A is our first endpoint, and then we have x1, x2, and then so on. We have n pieces until we get to xn equals b, like so. Okay, so each one is has delta x. The width is b minus a over n, and the endpoints are at a and b, and we've made a grid of these n subintervals. So we've chopped up our interval AB into n pieces. And the next thing we're going to do is, having chopped up our interval into pieces, into a bunch of subintervals, we're going to look at each subinterval. And here, for example, we have the kth subinterval between the points xk minus 1 and xk. And on each subinterval, we're going to pick a point from inside that interval, and we'll call it, say, xk star. So that's going to be the point, just an arbitrary x point inside that kth subinterval. And then what we're going to do is we're going to evaluate the cross-sectional area at that point. And so the volume of that slice is going to be the cross-sectional area at A of xk star times delta x. And so what we're doing is we're doing this. We are chopping up our interval into pieces, and on each subinterval, we're taking a cross-section. So we can cut our solid into slices. So we'll take a slice, and we're going to look at the cross-section, and we're going to calculate the area of that slice, like so. Okay, so we've chopped up our interval AB into pieces. Let me make this a little larger. Okay, so we've chopped up our interval A to B into pieces. We're going to, on the kth piece, we're going to evaluate cross-sectional area there. And so the volume of this slice, this blue slice here, would be A of xk star times delta x. Okay, now we've done that for all n pieces of the interval AB, and so we can approximate the volume by adding up these little volume slices. Okay, and of course, the more slices we have, the more accurate our approximation becomes. And so if we take the limit as the number of slices goes to infinity, okay, in such a way, this is kind of a side thing important for the math to work. You don't just take the slices to 0. If you do this particular partition, it works. So it also, by taking n to infinity, that also drives the width down to 0. So delta x also goes to 0. And the limit, as n goes to infinity, of this sum here, of the cross-sectional area times the width, is the integral from A to B of A of x dx. Okay, so that is what is called the general slicing method. The general slicing method is analogous to what we did when we built the Riemann integral in the first place. And It is also a technique that we're going to use over and over and over and over again. You will see it several times in Calc 2. You will see it a ton of times in Calc 3. It is a general strategy that works a lot. So our general slicing method is like so. We have a solid object that extends from A to x equals A to x equals B with a cross section of the solid perpendicular to the x-axis, and that cross section has an area given by a function a that's integrable on AB, then the volume of the solid would be the integral from A to B of A of x dx. So we can look at an example to kind of see how this is going to work. So the first example we'll look at here is the volume of, call it a parabolic cube. And so what this is R is going to be the region shown here, and that's the region in the first quadrant that's bounded by the coordinate axes and the curve y equals 1 minus x squared. Okay, so the solid then has base region R, and the cross sections through the solid. So what we're imagining is this thing kind of then extends up, right? So the cross sections of this thing, this parabolic cube here, have base R, and they extend up as a square slice, like you can see there. So we want to find, so the cross sections go through the solid perpendicular to the base, and the slices would be parallel to the y-axis. So they would look like the shaded blue right there. And so what that means is each slice is a square, and the length of that square is the distance from the x-axis to the curve y equals 1 minus x squared, which means each side has length 1 minus x squared. So if it's a square slice, then the area of that slice, okay, cross section square sides 1 minus x squared. The area of each slice is 1 minus x squared, quantity squared. And so our volume, using the general cross-sectional method, would be the integral from x equals 0 to x equals 1 of A of x dx. And so that's the integral from 0 to 1 of 1 minus x squared, quantity squared, dx. Okay, so we would just need to calculate that integral. This is one that we can do just by expanding, right? Getting rid of the parentheses there. And so that gives us 1 minus 2x squared plus x to the fourth. Okay, and then, if you, to refresh your memory on integrals, right, you do the antiderivative, and so that's going to be x, and that's minus 2x the cubed over 3 plus x to the fifth over 5, and then this thing is evaluated between 0 and 1, and so you're going to get 1 minus 2/3 plus 1/5, and that works out to be 8/15 if we find our common denominator. Okay, so that's our first example We can look at a second example here. Okay, but just to kind of jump to see what we're talking about, this parabolic cube idea, this was the volume that we were doing. Right, so the base was this region R, and the slices went perpendicular to the x-axis, parallel to the y-axis, and so it looked like so. Okay, but now we're going to look at a different shape for the next example. The next example, then, we're going to look at the volume of a parabolic hemisphere. And so this is a solid that has a base bounded by the curves y equals x squared and y equals 2 minus x squared. And so you see the plane there. You have your two curves, y equals x squared on the bottom, y equals 2 minus x squared on the top. And a typical cross section of this that goes perpendicular to the x-axis. So we're taking slices perpendicular to the x-axis. And you see the radius of each slice. So the typical cross section would be a semicircular disc. The area of a cross section of a semicircular disc is always going to be 1/2 pi r squared. So we just need to know the radius of the cross section. And for us, the radius of the slice is going to be the difference between the upper curve, y minus 2x squared, and the lower curve, x squared. Okay, so let me jump to my thing here. So we're saying the area of each cross section is going to be 1/2 pi r squared. And so we just need to know what r is. So where r is a function of x, and r for us, remember, so we have, here's the lower, and then we have this upper. And so the upper curve is the 2 minus x squared. So the area between the region here is going to be 2 minus x squared minus x squared. Okay, that's going to be r. So r of x is 2 minus x squared minus x squared. And so that works out to be 2 minus 2x squared. And so the area of our cross section then is 1/2 pi times r squared. And so that's 2 minus 2x squared quantity squared. Oh, sorry about that. It should be 1/2. Oh, sorry, I'm in Google up here. This should actually This actually works out to be 1 minus x squared because the area of the cross section is actually 1/2 of this. All right, so it's 1 minus x squared like so. And then we get to there. And so this then becomes pi over 2 times 1 minus x squared, quantity squared. And so what we're going to do is we're going to integrate pi over 2 times 1 minus x squared, quantity squared dx. But we have to integrate it over our region. And so we need to find the intersection points for our cross section here. Okay. And so we have the bottom curve, x squared. You have the top curve, 2 minus x squared. So this is x squared. And so to find the intersection points, we want to know, where does 2 minus x squared equal x squared? And so you get x equals -1 and 1. And so you would integrate between -1 and 1. Okay, so if we do that, you get, again, you're going to do the same thing as before. You're going to expand the parentheses. So you're integrating from -1 to 1, pull the pi over 2 out in front. And then you get 1 minus 2x squared plus x to the 4th dx. Okay, and it's the same basic idea as before, right? To the antiderivative, we'll just kind of skip that, and it works out to be, when you solve that definite integral, 8 pi over 15. All right, so it's the same, very similar to the first example. All right, next we move into the next technique. Okay, that was a cross-sectional, the general slicing method or cross-sectional area approach. And now we're going to talk about something called the disk method. And that leads us to a specific type of solid, which is called a solid of revolution. And the setup is like so. We have a curve, y equals f of x, such as the one shown in this figure here. Okay, so the curve y equals f of x, and the region R is bounded by the x-axis, the curve y equals f of x, and the lines x equals a and x equals b. And what we're going to do is we're going to take this region. We know how to find the area of this region, but what if we take this region and we spin it in 3 dimensions about the x-axis? And if we do that, then we get what's called a solid of revolution. All right, so we get something that looks like, like the nose of a bullet, say, or nose of an airplane, maybe, however, whatever you want to think of. But that's the idea of a solid of revolution. Take a region like we've just described, spin it about the x-axis, you have a solid of revolution. Okay, and you can do that about the y-axis also, but we'll just start with the disk method about the x-axis. So we generate a solid of revolution like so. And now we're going to do the same thing, which is we're going to say, all right, well, let's look at a slice of that. Okay, this solid that we've built, let's take a cross-sectional slice and see what that looks like. And then we can add up a bunch of those cross-sectional slices, and that'll tell us what the volume is. Okay, so the cross-sections of a solid of revolution are circular disks, with the radius of that disk is our function that we started with, f of x, right? That's the radius. So at each point, the cross section of a solid of revolution is a circular disk. The radius is f of x, and of course, the radius of a circle is r squared times pi, and so that would be pi f of x squared. And once again, if we add up a bunch of those slices and we do it in such a way that as we drive n to infinity, we drive delta x to 0, and once again, we get an integral. So the disk method about the x-axis looks like so. We have a continuous function, f of x greater than 0 in the interval a, b. The region R is bounded by the graph of f, the x-axis, the lines x equals a and b, like this diagram here, region R. And we revolve that region about the x-axis. The volume of the resulting solid of revolution is the integral from a to b of pi times the radius of that disk, which is f of x squared dx. So we can do an example here where we have f of x equals x plus 1 squared. And we're going to take the region bounded by the x-axis, the curve f of x equals x plus 1 squared, and the lines x equals 0 and x equals 2. We're going to form a solid of revolution like so. And so the just jotting down what it is there. Okay, so we're going to form a solid of revolution like so. And the volume of that thing then all right, so the volume of that solid of revolution is the integral from 0 to, I think we said 2 in our example. And f of x, that's our radius, so it's going to be x plus 1 quantity squared, and so that would be x plus 1 to the 4th dx, and times, don't forget the pi, because it's a circular. And so we would, once again, this is a good case. If you look at this, you don't want to, you could expand this out. It would take you a while. So I recommend our friend a u substitution. We say u equals x plus 1. Du then is the x. And so the volume here is pi times the integral of u to the 4th du, but remember, you got to change bounds if you're going to do that. So when x equals 0, u equals 1. When x equals 2, u equals 3. Okay, and so that is pi times u to the 5th over 5, evaluated between 1 and 3. And that will give you 242 pi over 5 as your final volume. Okay, so that is the disk method. Now let's look at a variation where the region R. Okay, so before, right, we had our curve f of x, and the region was, right, bounded by the x-axis. But instead, now let's suppose that I have another curve g of x. And so R, instead of being by bounded by the x-axis is bounded by an upper and a lower curve, what would you do then? Okay, and that is what leads us to the washer method. Okay, that's what leads us to a washer method. So let me jump over to here. Now, the washer method is, like we said, we have an upper curve and a lower curve, and we're looking at the region between the curves. Instead of the bottom curve, if you will, being the x-axis, it's another curve, g of x. We're doing the same thing. We're going to revolve that region r about the x-axis, and that gives us a solid, still a solid of revolution, but now it's one that has a hole in it. So when we look at each cross section, whereas before we jump over to our thing before, so before our cross-sectional area, right, A to B, and here's the x-axis, and this was what we were doing before. What we were basically doing, our cross sections or pieces were like this quarter here, right? So we were just looking at discs like this of varying radii, and that's what we were adding up to find the volume. Now, in this scenario, our cross section looks like this. It looks like a washer instead of a quarter. Okay, and so we're stacking up in cross section slices that look like washers, which is why, again, it's called the washer method. So in that case, the cross-sectional area, okay, if you're finding the area of this disc, right, this washer, there's an inner radius and an outer radius. And so what I do is I find the area of the whole thing, the outer radius, and then I find what the area of the hole would be, and I subtract that out. And so that's what our cross-sectional area is. So it's the outer area is r sub 0, the inner area is r sub I. So the cross-sectional area is the area of the big disk, pi r0, or sorry, RO for outer squared, minus pi r sub I squared for the inner, and that is our cross-sectional area. And so what we do is we take the cross-sectional area, pi times, now the inner radius is given by that bottom curve. If we go back to our picture here, the bottom curve, g of x, the outer radius is the upper curve, f of x. So our cross-sectional area is pi f of x squared minus g of x squared. And we're going to integrate that from A to B to get our volume. Okay. Do not note here it's f of x squared minus g of x squared. It's not quantity squared. Easy mistake to make, right? You're finding the area of the outer disk minus the area of the inner disk. Okay. All right. So the washer method rolled up like so. F and G continuous functions with f of x greater than or equal to g of x greater than or equal to 0 on AB, like our picture here that we showed. Okay. R is the region bounded by y equals f of x, y equals g of x, and the lines x equals a and x equals b. If we evolve that region about the x-axis, the volume of the resulting solid of revolution is the integral from a to b of pi times the quantity f of x squared minus g of x squared dx. Okay, so let's do an example here. We'll look at the region bounded by the curves f of x equals the square root of x. The lower curve would be, in this case, is g of x equals x squared. from x equals 0 to x equals 1. Okay, so the outer radius is the square root of x. The inner radius is x squared. The interval, so it's the region bounded by those two curves. And so we need to find where does x squared equal the square root of x. Okay, that happens at x equals 0, and it happens at x equals 1. And so our integral goes from 0 to 1. So if we revolve this, it produces a bowl-shaped solid like so. And so our cross-sectional area, let's jump to this whiteboard here. The cross-sectional area. Okay, so the outer one was the square root of x, and so it's right square root of x squared minus x squared squared. Both of those times pi. Okay, so then this works out to be pi times x minus x to the fourth as our cross-sectional area. And so what we'll do, the volume then goes from 0 to 1. Pi times x minus x to the fourth dx. And x squared over 2 minus x to the fifth over 5. All right, evaluated between 0 and 1. And that works out to be 3 pi over 10 precisely. Now, both the disk and the washer method can be expressed in terms of revolving about y instead of x. Okay, so we described a solid of revolution as a region where we're spinning about the x-axis. Well, you can do the same thing with a region that you spin about the y-axis, where now the cross sections are perpendicular to the y-axis instead of perpendicular to the x-axis, and the slices run parallel to x instead of y. Okay, so it's just the same setup, but now the slices are perpendicular to y instead of x. The concept, everything's the same. All we're doing differently is now we're going to integrate with respect to y instead of x. So here's our setup. Let me make this a little larger here. Okay, so now we have a region bounded on the upper side, so that would be on the right by a curve, say P of y, and bounded on the lower side on the left by a curve Q of y. And so now the outer radius is P of y, and the inner radius is Q of y, and we're going to be integrating along the y-axis instead. And so we take that region, okay, bounded on the right by P of y, on the left by Q of y, and we're spinning that region, rotating it about the y-axis to form a solid of revolution like so. The outer radius, we said, is P of y, the inner radius, Q of y. And so our washers, our slices, are would be pi p of y squared for the outer disk minus pi q of y squared for the inner disk. And so the disk and washer methods about spinning about the y-axis are basically the same, right? It's still the upper minus, the max minus the min, the outer minus the inner, right? But now we're integrating along the y-axis. We're going to get with respect to y instead of with respect to x, but the idea is the same. The approach is the same. And so let's look at a quick example here. Okay, so in this example, we'll have a region bounded above. So in this case, that is on the right by the curve. So the outer radius, right, by the curve 4y, and bounded on the left. So the inner radius would be the curve y cubed. And we're going to take the region between those two curves. And so if we want to find the points of intersection, we set them equal to each other, and you get 0 and 2 as your two points of intersection. And so we're going to integrate that like so. So from 0 to 2, pi times the outer radius 4y quantity squared minus the inner radius y cubed quantity squared dy. So that works out to be 16y squared minus y to the 6th dy. So that's pi times 16y cubed over 3 minus y to the 7th over 7, evaluated between 0 and 2. Okay, and you can plug that into your handy dandy calculator. The lower limit's obviously going to be 0, and so it's just 16 times 2 cubed over 3 minus 2 to the 7th over 7, all times pi, whatever that reduces to. So that's our example of the washer method of a solid of revolution about the y-axis. Now we can also, the final thing for this topic is, what about revolving about other lines? So lines other than the two axes, what do you do? All right, so let's look at that setup real quick. So in the case of a solid of revolution, where now the region is, we're not going to spin it about the x-axis, say maybe we want to revolve it around another line. Like, let's look at this particular example here. We have the line y equals 2. So instead of y equals 0, the x-axis, the line we want to revolve around is the line y equals 2, and the region is the region bounded by the line y equals 2 and the curve y equals the square root of x plus 1. The idea is still the same. Okay, you want to take a cross section, you want to figure out what the radius looks like. Okay, and that's what you're going to work with. Okay, so in this case, what is the radius? Well, it's a difference between the line y equals 2 and your curve. Okay, so the radius is going to be 2 minus the curve, all right, minus the y given by the curve. So that's going to be square root of x plus 1. So the radius in this case is the line 2 minus the square root of x plus 1, which works out to be 1 minus the square root of x. and everything else is just the same. Where do those things intersect? Okay, well, we have x equals 0, and we have x equals 1, right? All you do is you set y equals 2 to y equals square root of x plus 1, and you get 0, and you get, you can kind of see from the region, 0 is one of them, and for the other one, you get x equals 1, and you integrate that cross-sectional area from x equals 0 to x equals 1 to get the volume. So same idea. What's the area of a cross section look like? Let's jump to the whiteboard here. Okay, what does the area of a cross section look like? It looks like 1 minus the square root of x, quantity squared times pi. It's a disk, so pi times the radius squared, which is 1 minus square root of x squared. And so the washer method says we're going to integrate that from 0 to 1 in this case. Like so. Okay. You could do that particular one by whatever method you like. I'd expand this. So pi integral 0 to 1, you're going to end up with 1 minus 2 root x plus x. Okay. And remember, square root of x is the same as x to the 1/2. So you can do the power method there. And so this is pi integral 0 to 1, 1 minus 2x to the 1/2 plus x dx. And so you can use the power method on all of those. So x to the 1/2 plus 1. So that's x to the 3/2 divided by, so that's and divided between 0 and 1. And I think that works out to be like pi over 6. Okay. All right. So that is the volume by slicing. Okay. So that's calculating volume by slicing, both for cross-sectional areas. The idea is the same, whether you're talking about solids of revolution or the other type, which is find what the area of a cross-section looks like, and then add all of those up. Okay, you're integrating along some axis, find out what the cross-sectional area looks like, and integrate along that axis. And if you integrate the cross-sectional area along the appropriate axis, you're going to get the volume. Okay. All right. So that is it for the first section. Let me know if you have any questions. And also let me know when you get your schedule, and we can tailor it to be more tied to your schedule.